Hello and welcome to particle interactions. Okay, so we know that there are four fundamental forces or interactions: gravity, electromagnetic, the weak, and the strong nuclear forces. Forces allow particles to interact with each other, but in order to do this, they exchange force carriers or exchange particles. Now, on this course, we're not going to be talking about the gluon, we're not going to be talking about the Higgs, and we're not going to be talking about the Z boson, but we are going to be talking about the photon and the W plus and W minus bosons. Okay, first thing we're going to talk about though is the photon, which is the exchange particle or the force carrier for the electromagnetic force. That's the force responsible for attraction, repulsion, annihilation, and pair production. Now you remember that a photon or light has two components to it: the electromagnetic, consisting of the electric, and the magnetic, and they are at 90 degrees to each other, and you might be familiar with a diagram that looks like that. Okay, so that's why it's easy to remember the photon, which is an electromagnetic wave, is the force carrier for the electromagnetic force. So let's have a look at some simple diagrams to demonstrate what is going on when the following things are occurring. Okay, so first things first, attraction. If we have a positively charged proton and a negatively charged electron approach each other, they are going to exchange a photon with each other, and that will cause them to attract. Now this diagram, this simple diagram, shows the movement of the proton, the electron, and the force carrier. It does not show their proximity to each other. So we know that once this exchange particle has been exchanged, they're going to be attracted to each other, they're going to move towards each other. But in terms of their interactions, this is it. So in terms of this diagram, the electron is going to move away because there are going to be no further interactions, and so is the proton. So they are entering our consideration and then they are leaving our consideration. The attraction between them has been explained by this interaction here. So this diagram did not demonstrate their proximity, their closeness in physical space to each other. It just shows that they are approaching, an exchange particle is exchanged, and that's it. That's all the interaction that there is. It's a very similar diagram with repulsion. Let's do two protons. So we have a proton approaching another proton. They interact, and that's it. Okay, so there we have repulsion. Annihilation, that's when a particle and its antiparticle come together and cancel each other out, and they disappear, and we just get the pure energy from their masses. So let's do that with a couple of particles. Let's choose the electron and the positron. So in this diagram, this is very different from what we've seen previously. They are arriving at the same location at the same time. So these are going to meet each other. And when that happens, they annihilate. Their masses turn into pure energy in the form of a photon. So that's annihilation. Those particles no longer exist. They have turned into this photon. And the energy of that photon is going to be equal to the energy that comes from their masses, which you will be studying later using this equation. Okay, but not yet. Pair production is the opposite of annihilation. You start off with a photon, you start off with energy, and at a certain point, it will generate a particle and antiparticle. Let's use the electron again, electron and a positron. It's nice and simple. So there we have pair production. So that photon had exactly the right amount of energy, exactly, in order to create these two electrons, the electron and the positron, or the electron and the anti-electron. So that photon there will have had exactly the right amount of energy to generate those two. So that's pair production. Okay, on to W bosons. Now the W bosons are the force carriers for the weak interaction, or the weak nuclear force. And the weak nuclear force is responsible for beta decay, and it's responsible for a couple of other things as well that we're going to talk about in a moment. So beta decay is what happens when you get the nucleus of an atom becoming more stable because either a proton or a neutron is decaying into something else. So when there is an imbalance between the protons and the neutrons inside, then inside the nucleus, then what we're going to get is we're going to get either beta minus or beta plus decay to stabilize the nucleus. In beta minus decay, what we're going to have is we're going to have a neutron splitting into a proton and an electron. So this neutron turns into a proton inside the nucleus. So this neutral particle is going to split into its positive and its negative parts. And the way it does that is in two stages. So first of all, the neutron turns into a proton and it gives off a W minus boson. And this carries with it the negative charge. So you can see we've got a neutral object splitting into a positive and a negative. This negative object decays further into our negative electron, which is the beta particle that is given out from the nucleus, and also its antineutrino. So that's beta minus decay. Beta plus decay is when a beta plus particle is given off, and instead of it being an electron, it's a positron. So we are giving out a positive charge. And the way that that happens is that a proton becomes a neutron, so it loses its positive charge. That positive charge is carried away by a W plus boson, which decays further into our positron. There's that positive charge being carried away, and a neutrino. Okay, there are a couple of other things that you need to know about in terms of the weak interaction. So there's beta minus and beta plus decay. We also need to learn about electron capture and electron-proton collisions. So electron capture is what happens when you have a nucleus with electrons orbiting around the outside, and the electron is captured and absorbed by one of the protons inside the nucleus. So what this does is it's another way for the number of protons inside the nucleus to be reduced. The electron-proton collision is when a stray electron collides with a proton, and it's a very, very similar thing. So let's have a look at electron capture. So we have our proton inside the nucleus, and we have our electron outside the nucleus. And what happens here, and what I'd like you to imagine happens, is that the proton reaches out to grab the electron. That's the easiest way to imagine this happening. And it does so through the mechanism of a W plus boson. The W plus boson produces our neutrino, and the proton absorbs that negative charge and turns into a neutron. Electron-proton collision is exactly the same process, except instead of a W plus boson, it's a W negative boson. So our proton and our electron are going to collide. The electron, there's the electron, is the initiator in this example, and we get the same